Good day, grade 12 chemistry students. Today what we're learning about is electron configurations. There is actually two types of electron configurations, well, plain old electron configurations and something called energy level diagrams. We are learning rules called the Pauli exclusion principle, Hund's rule, and Aufbau principle, and they're going to help us make these electron configurations, and we're going to see how they relate to the periodic table. Here we go. So we have Bohr's model, which worked really well for hydrogen, but didn't work well for the other elements. So if we take a look at Bohr's model on the left here and quantum mechanics model on the right, we're going to compare it for sulfur atom. When we look at a sulfur atom, sulfur is located right here. Okay, now sulfur has an atomic number of 16, so that means it's got 16 electrons. That means normally, according to Bohr model, it would be filled up like this. As you can see, the Bohr model here, we have 16 electrons, 2, 8, that's 10 electrons, and 6 more, that's 16 electrons. The first shell would be called n equals 1. Okay, that's the first shell, second shell, and third shell. So really what Bohr knew about was the principal quantum number, okay? And the principal quantum number, which is n, which represents what shell that electron is. So when we looked in the third shell, we can see that we have 6 valence electrons. Now with quantum mechanics, we no longer think about electrons being in orbits. We think about them being in orbitals or three-dimensional space. So quantum mechanics still has the periods. It still recognizes the first quantum number, which is represented by the letter n. So hydrogen and helium, they both have electrons. Their only electrons sit in the first period. You have the second period, which is n equals 2, n equals 3, and so on. But quantum mechanics takes it to the next level. It says that there is sublevels, which we call L. Now, L really means the different types of three-dimensional shapes where these electrons can sit in. So in the first period, helium is actually considered to be over here. We say that this is our S block. Now our S block, really what that means is L is equal to 0. We just assign it a number. So L is really the subshell energy level, and L is equal to 0. We also have, so after we fill the first shell, we have a second energy level here, second shell, which is also in the S block, which is also a sphere. Over here, once we fill the second energy level S orbital, we start hitting boron here and going across the periodic table like this. This is what we call the P block. So the P block is all this area right here, and its L is equal to 1. Now we can fill these guys up, keep filling them up. We fill after we fill up the 2p orbital, we start filling up the third energy level. Now the third energy level takes a brand new S, okay? And then we have another p orbital. Now what you need to know so far, I've just introduced S's and P's and I've given them numbers. L is the second quantum number or sub-energy level, and they have different shapes. So all you need to really think about right now and know is that they have different three-dimensional shapes. Electrons are no longer in just simple orbits. They're in orbitals, which are three-dimensional shapes. So I'm going to show you what sulfur looks like. So if we take a look at sulfur, which is located right here, I know that's going to be difficult for you to see, but it has 16 electrons. So let's take a look what it looks like when we fill up our electrons. So in our first shell, just like Bohr's model, we hold 2 electrons, but now they are no longer in a simple orbit. They are in an orbital, an S orbital. And S orbitals look like spheres. So I'm going to draw an arrow going up and an arrow going down. Now electrons like to be in pairs and they like to have opposite spins. So we're actually seeing spin here. So we have 2 electrons in a sphere-shaped orbital. That's the first shell. This is n is equal to 1. Now we know we have more electrons than this. But at this point, we've actually filled up the first energy level, okay? Just one S. Now we're going to start on the second energy level. Remember, we got to get all the way over to sulfur. So now on the second energy level, we are still in the S block. The next 2 electrons get placed in an s orbital that is quite a bit larger in the second energy level. N equals 2, but again, L is equal to 0 again because it's an s orbital. So the second s orbital is actually a lot bigger than the first. And this just tells us the approximate area. And it actually fits right over top of the first s orbital and is a lot larger. Now this is the second energy level. The question is this energy level full with 2? Well, you remember the second energy level of Bohr, it actually holds 8. So we're not done yet. This is just a sub-energy level. There is going to be another orbital that fits over top of this, which is just slightly larger, which is going to hold the other 6 electrons. This p orbital is actually made up of 3 suborbitals. If you can see here, this is 1 dumbbell, 2 dumbbells, 3 dumbbells, and it actually holds 6 electrons. Now each one is just slightly larger than the previous s orbital, so it's still considered to be in the second energy level, but it has slightly higher energy. We assign this a secondary quantum number L equals 1. Recall that the s was L equals 0, so the p orbital is L is equal to 1. But you'll also notice that you actually have 3 different types of suborbitals in here. Each one holds 2. So orbitals always hold 2 electrons. So we have to assign a third quantum number which describes what type of orbital it is in. So it can be actually located in 3 different orbitals in this p orbital. We call this the ML value, the third quantum number, and it can represent either for L, there's actually 3 options, -1, 0, or 1. I will explain where these numbers come from in the future, but each orbital, this one here, it looks like 1 dumbbell would be considered -1. This one here could be considered 0, and this one here could be considered +1. Now there is no way to know which one is which. We just know that there's 3 of them, and I'm just assigning these at a random time right now, but I will explain a little bit later where they come from. Now in this energy level, we know it's full of 8 electrons. So I'm going to place the electrons in here, and watch what I do. I'm going to half fill each orbital before I pair. Okay, so I'm going to put 1 electron with 1 spin in each one, and then we are going to pair up the other electron with it, and it's just going to be spinning in the opposite direction. So again, this is going to represent a different quantum, the fourth quantum number, which represents spin. So these quantum numbers, what they really allow us to do is they tell us a lot about any individual electron. They tell us the energy level that it's in, they tell us the type of orbital it's in, they tell us which exact orbital is it within that suborbital, and they give us a spin. Now the spin can either be positive half or negative half. Don't ask me why, grade 12 students. It's just they equal out to be 0. One has a positive half spin, one has a negative half spin, they equal 0. So at this point we've completely filled up this subshell here. What happens next? Well, we've taken care of 8 electrons. We said that the 1s2 was our first orbital, which was an s orbital with 2 electrons. And then we had something called the 2s2, 2s orbital with 2 electrons in it. Then we just took care of our p electrons. So as we go across, that held 6. Now we're going to add another s as I go across the periodic table, which is going to be even larger. So this represents the 3s, which is even larger, and again it holds 2 electrons, so we place 1, and then we place another one. At this point we are almost there. We placed 2 more electrons, we have a few more to place, 4 more I believe, so let's take a look at our periodic table. So these 2 electrons were in the 3s orbital, n equals 3. We have 4 more electrons to place in the p. So if I was going to give any of these 2 electrons, before I continue any quantum numbers, we would say that this is the third energy level. We would give this an s orbital, so it's L is equal to 0. The ML value for this is the suborbitals. You can only see that there's one type of suborbital in an s orbital, so we actually give it a 0. I'll explain where that comes from. And you could give it a spin, depending on what electron we're talking about, either a positive half spin or a negative half spin there. But again, we don't care about those quantum numbers. We're not completely full for sulfur. We know that it has 6 valence electrons. I have drawn 2 here. That s orbital is full. I still have to put 4. So that means we need a p orbital that is larger than that s, because it's higher energy as we go across the periodic table. And we have to place 4 electrons here. So I have 4 more electrons to place. Again, the L value of these 4 electrons is L is going to be equal to 1. We are then going to, since there's 3 p orbitals here, they all have similar energy. So before, I can't just pair them up. I have to half fill each one. So what I'm going to do is put 1 electron here, 1 electron in this orbital. I'm just putting it so I've taken care of this one. 1 here. And I have 1 left to place, and I can pair it on any one of these. They are all equal energy, so I'm going to pair it here. So this orbital right here, it's actually both sections. Those electrons can exist in either zone there. That is full. So this leaves 2 orbitals for sulfur to be available for bonding. Okay, so the ml value of those, again, the full one might be -1. I'm just guessing. It doesn't matter which one it is. And the other 2 could be 0 and 1. So that's just the assigned number for each one of these suborbitals. And the spin, again, could be +½ or -½ So let's go through this quickly, and let's look at the periodic table, and let's see if we can find what we call an electron configuration. An electron configuration gives quantum numbers for all the electrons that you have present. So the way we determine the electron configuration is we say, okay, sulfur is here. Its first 2 electrons were like hydrogen and helium. They fit in an s orbital, so we call that 1s2. I'll show you how to write that out. The next 2 electrons fit in the second energy level. It was 2s2. The electrons after that were still in the second energy level. We call it 2p6. The 6 means that there was 6 electrons held in there. The next energy level gets filled here, and it's 3s2. So it's the second energy level, third energy level, and it's in an s orbital, and there's 2 electrons there. And then we finish off with 2p4 because it's not completely full. So this is the electron configuration: 1s2, 2s2, 2p6, 3s2, 3p6. The numbers represent the amount of electrons. Now this is the first energy level, so the number represents the n value, or the principal quantum number. The s and the p represent the L value. When it's an s value, an orbital s, we said it was assigned a letter 0. When it's a p, it's assigned a letter L. Okay? So you can see that s and p would both have different numbers and different orbitals. If I was asked to highlight the valence electrons, you'd look, it's still the highest energy level. When we looked at the Bohr, it should have 6 valence electrons. When we look at this diagram, it still has 6. It actually should be 3p4 there, my bad. It actually is, the 6 electrons are here. So in the third energy level, you have an s orbital with 2, and then you have a p with 4. These are the valence electrons. So this is called an electron configuration. And what it does is it tells you 2 quantum numbers. That's it. It tells you the principal energy level, or the shell that it is in, and it also tells you the type of orbital that each electron sits. You also can determine the valence electrons from this. So we have a question here. It says determine the electron configuration for calcium. What we would need to know is we'd need to look at the periodic table and tell the first 2 principal quantum numbers for all the electrons. So for neutral calcium, I just write Ca ... and then I would go and look at the periodic table. Looking at the periodic table, we can see calcium's at 20. I have 20 electrons to place. When I look at the periodic table, I would say, okay, my first 2 electrons starting at 1 and going all the way to 20. So I go 1, 2. So helium is considered in the s block, so I would go 1s2. Then I would continue on to the second energy level, and I'd write 2s2 because this is still the s block. I would go over to the p block, and I'd say 2p6. Continuing on to 3s2, 3p6, past sulfur, which we just completed, and then finally, what next, folks? 4s2. That's correct. Let's write that out. So we will stop right there. We will never do 1 past calcium until tomorrow for this video, because we are now hitting what we call the D block, and something special happens there. We'll talk about this tomorrow. But if we write out the electron configuration of calcium, it looks like this. Sorry. Here we are, and again it shows the first two quantum numbers, 1 through 3, sorry, all the way to 4. That is your principal quantum number. The S is the L value, or the second S and P is the L value or the second quantum number, and the number at the top just represents how many electrons are in each one. If asked to underline the valence electrons, I would just say this, and calcium has 2 valence electrons, and they are located in the 4th energy level in an S orbital, which is full. And that's it. What I'd like you to do for me, please, is try and draw the electron configuration for something smaller than that. Let's do fluorine. So show me the electron configuration for fluorine negative. I'm actually going to make it more complicated. It's not fluorine anymore, folks. It's fluoride. Put a D on there. Do that. Add 1 electron. Please tell me the electron configuration for fluoride. What is it isoelectronic with? So that's it for now, folks. Hope to see you tomorrow, and we'll talk about it more. Thank you very much.
This is that ice cold Michelle fight for that white gold. This one for them hood girls, them